Theorem 4 is designed to find the probability of A or B when they're not mutually exclusive. So here is an example of not mutually exclusive. The events that are not mutually exclusive have some outcomes in common. So this is a rule of thumb. For example, a dice is rolled. Therefore, my sample space is 1, 2, 3, 4, 5, 6, right? And the event A is defined as an even number is obtained, so A equals to the 2, 4, and 6. A collection of the outcomes, also a subset of the sample space, right? And then event B is defined as a number smaller than 4 is obtained. Therefore, the event B equals to the set of outcomes containing 1, 2, and 3. So here, this square, this blue square stands for our sample space, all these 6 outcomes, and this white circle stands for the event A. So event A comprises the 3 outcomes, and this event B comprises these 3 outcomes. So now, as you can see, the outcome 2 occurs in both event A and event B, right? So now you cannot tell. So if I said that event A occurs, if I said that an even number occurs, then you cannot say for sure that event B will not occur or event B will occur, right? Because they have this overlap in the number 2. Event A and event B are not mutually exclusive, then the probability of either event A or event B or both is given by this formula. So the PA or B or both of them will happen equals to the probability of A plus the probability of B, and then minus the probability that both of them occur. So note that the theorem 3 is actually a special case of theorem 4 when this P both is 0. Okay, so if A and B are mutually exclusive events, then they have no overlap outcomes. So the probability of both A and B occurs 0, and therefore it leaves the theorem 4 to be the same as theorem 3. And if A and B are not mutually exclusive, then there are some outcomes, right, that are overlapped here. So if you use PA plus PB, then this shaded area are counted twice. So it was counted in the PA, and it was also counted in the PB, right? So if you want to compute the probability of A or B or both of them happen, then you should minus 1 round of this shaded area, because it was counted twice, so you need to minus 1 times of counting this shaded area of this overlap outcomes, and therefore you need to use PA plus PB and minus the P both. So when they are not mutually exclusive, the P both is greater than 0. The PA and B both happen, both occur, is not an empty set, right? It contains some outcomes here, so the PA and B are greater than 0. And here's our example 7.5 for the not mutually exclusive example. So if I randomly select a part, what is the probability that the part is form X or non-conforming? So now we can see that the part form X comprises of 50 conforming parts and 3 non-conforming parts. And also there are 11 non-conforming parts. So if you take these 2 sets, right, this 53 parts form X, and then this set defines the event B, the non-conforming parts, then you can see that there is an overlap in these 3, right? So the parts that are both from supplier X and non-conforming, so the non-conforming units from supplier X is the overlapped outcome, right? So we have 3 outcomes here in the shaded area. And therefore, if I wanted to compute the probability of either this one is happen, or this happen, or both of them happen, then you should use Px plus the probability of non-conforming parts, and then minus the probability of non-conforming parts from X. Okay, so the Px, as we discussed before, is this 53, right? The number of outcomes that make event X to be true is 53, and then divided by the size of our sample space, 261. And then the probability of non-conforming parts is the total number of non-conforming parts, so 11 out of 261 out of the all possible outcomes, and then minus the probability of the non-conforming parts from supplier X. So here we have 3 non-conforming parts from supplier X. So we use 3 divided by the 261, and this gives us the probability of this overlap, right? And then this gives you the final answer is 0.234. Theorem 5 states that the sum of the probabilities of the events of a situation is equal to 1. So this is like when you are facing a situation, when you implement an experiment, then you are facing a situation that can be divided into mutually exclusive events, and therefore the sum of all these possible events will be 1. So Theorem 5 has a very intuitive interpretation. For example, if you toss a coin, then the probability of getting a head plus the probability of getting a tail is 1, right? 1/2 plus 1/2 is 1. And if you roll a dice, then the probability of getting 1 spot plus the probability of getting 2 spots and up to getting 6 spots will equal to 1, right? And when you draw a card from a deck of cards, then the probability of getting these 4 suits, if you sum up the probability of these first 4 suits, then that will be 1. Here's the example 7.6 from our textbook. So a health inspector examines 3 products in a subgroup to determine if they are acceptable. So out of these 3 products, there are only 4 mutually exclusive events. So there could be 0 non-conforming units, or 1 non-conforming units, or 2 non-conforming units, or 3 non-conforming units. So I already know the probability of getting 0, 1, or 2 non-conforming units from the statement. And then it asks for what is the probability of finding 3 non-conforming units in this sample of 3. So that means all these 3 products that I picked are non-conforming, right? And therefore the P3 is just equals to the 1 minus P0 minus P1 and minus P2.